function f of x, y, z is x times z. And we want to compute the triple integral of this function where e is bounded by the plane x equals 0, y equals 0, z equals 0, and this plane x plus y plus z is equal to 1. Right. So what do you end up getting? And it's very important, especially in 3 dimensions. You kind of get away with not doing it in some cases with double integrals. With triple integrals, it becomes more and more important to visualize the solid that you're integrating over. And to do that, some of the things that you can do are what we talked about the second day of class, using a method of sections or level curves or something like that. Sometimes those can give you an idea as to what the object looks like. So if we have the plane x plus y plus z is equal to 1, we can figure out a few points that belong to this plane. So we need this one, x is 1, y and z are 0. Here we have x is 0, y is 1, z is 0. And this one, 0, 0, 1. So it takes 3 points to completely determine a plane, and these 3 will do it. And the planes x equals 0, y equals 0, z equals 0 also bound this solid in addition to this triangle here. So we have a tetrahedron where we have this triangle right here, this triangle sitting in the xy plane, and then this triangle in front. So we need to come up with limits of integration that allow us to integrate whatever function we have, in this case x times z, over that entire triangle. Now, in order to do something like that, you can try various approaches. For instance, is your solid bounded by the graphs of 2 functions of x and y, where x and y belong to some 2-dimensional region D that would be in the xy plane. In this case, the answer is yes, because you can think of this tetrahedron as being bounded below. So it's, on the bottom, you have the function z equals 0 that defines the base of a tetrahedron. And then the top, so this front triangle here is, I kill myself tripping over this thing. All right. Is defined by this function. I'm just going to take the equation for this plane here, and I'm going to solve it for z in terms of x and y. So z is 1 minus x minus y. So, the region D in this case is, actually I won't write it here, put it over here where I have room. So now if we're looking from above onto the xy plane, this is our region D. This is the base of our tetrahedron. So what we can do is describe our triple integral as, so we'll do the iteration one step at a time, as a double integral over this triangle, and then our inner integral with respect to z will go from our lower bound, z equals 0, to our upper bound, when z equals 0, just put 0, and 1 minus x minus y is our upper bound. We'll integrate our function with respect to z So that's our innermost integral. And then what we get from this will now carry out a double integral over this triangle. So at least we're taking this one variable at a time, trying to reduce a triple integral to an easier to handle double integral. All right. So now, instead of dealing with tetrahedron, we're now dealing with a triangle. So we can choose whatever approach we like to integrate whatever we end up with over this triangle. We can view it as a region of type 1 or type 2 or whatever you want to do. So what would be appropriate limits of integration to integrate anything over this triangle? You can go for a triangle, you can go in either order. You can choose limits on x first and then choose limits on y, or you can go the other way around. Sometimes you don't have a choice, but here you do. Say if we wanted to go with x first. So if this is how a triangle is defined, these 3 points, what would be, if we want to integrate a function over this triangle, what would be the appropriate limits in x? Yeah, from 0 to 1. All right, so those will be the outermost limits. So for each x between 0 and 1, what are the limits in y? Well, those would be upper and lower bounds. Now, you can start at y equals 0. Here's x equals 0, and here is x equals 1. So we can start at y equals 0, but we're not going to go all the way up to y equals 1, are we? Yeah, 1 minus x. So now we have all of our limits of integration. So our iterated integral will be, the outermost variable will be x. Our second variable will be y. And then finally we have z.
Why would this be 1 minus x?
Oh, because, if I pick any point x between 0 and 1,
Right.
the extent of a triangle will be from here up to here.
Okay.
And this line has the equation x plus y is equal to 1.
Okay, that makes sense.
Yeah. So often this is what you need to do is if you have a region like this that has edges being line segments, then you'll want to come up with equations for those line segments, especially if it's something that is difficult to simply eyeball. Okay. All right. So any questions? So this is the most important part, and yes, in terms of assigning points too on tests, for triple integrals, the setup, because it's more challenging than for double integrals. So any questions about how we first got from the tetrahedron to the triangle and how we handled the triangle?
How'd you get 1 minus x again?
Oh, from this equation. So I solved for y.
Right, but
Where'd the equation come from?
Well, you can use these 2 points to get the equation of a line, if all else fails. So you can use these 2 points to get your slope and do point slope form to get the equation. If you had a nastier example, just some triangle somewhere in space, and you were given the locations of these vertices, that's what you had to do. You had to come up with the equations of each of these edges. So for your limits of integration, you could do something like this from x equals a to x equals b, and you can get a and b from your vertices. And then for each x between a and b, then to use the equations of these edges until you got to here. Then you'd have to use equations for these 2 edges. So you can see that this can quickly get pretty tedious. So you got to be really careful about understanding what defines